started talking about yesterday was the first algorithm for constraint optimization, projected gradient descent. Okay. So far, we just gave you the basic definition. We saw how you start with gradient descent and do one small update or modification to it rather, which is that once you do your usual gradient descent update, you also do a projection operation. That's it, right? And the projection operation is itself a optimization problem, right? Given that there is some constraint set, feasible set, find me the point in the set which is closest to my target point. That's the projection operation. Okay. So we'll continue talking about it now. So we have defined let's say x star. Okay. So what does this mean? Projection of the point x star due to the feasible set omega. And how would I define it? Argument x can roam around on the entire set. This half is there just for convention, x minus x star. Right? This is the problem that I have to solve. This problem may or may not be simple depending on sigma, right? So we'll just make a few notes. PGD is useful only if the projection operation is easy to compute, right? So only if P sigma is easy to. It can often happen that the projection operation itself is very, very difficult or resource intensive, in which case you should not use this algorithm. Okay. There is another very nice property of this projection operation, which is a special case when sigma is a convex set. Okay. So this makes our life very easy, or rather I should say simple, that if my constraint set is a convex set, then if I do the projection operation, if I solve this problem correctly, the point that I get is unique. Okay. So this is something that is going to be very useful for me. Okay. So what does it look like graphically? Let's look at it graphically. So let us say this is my set omega. This is the constraint set. That means x should live in the interior of this, interior or boundary of this. Okay, so let us say this is my point, let's call it x naught, is over here. If my point x naught is over here, and I ask you what is this? What is the nearest point to x naught within omega? X naught, right? So that is the trivial, very easy case for me to deal with. Okay. Now let's take a point over here, x1, and the question I'm asking now is, right? That's what I want to know. So at least from a graphical perspective, how do you think we should start solving this problem? You see the definition of, you see the algebraic definition. This simply means find the nearest point in omega to my target, my candidate point. Okay, so that is the geometrical meaning of this. Now I'm at x1. I want you to find me the nearest point from omega to x1. Right. So think of yourself as high school geometry with protractors and all of those things. How would you solve this problem? I don't think you knew grad C in class 9 or 10. Perpendicular means, so I have a scale and what am I doing? Okay, that is correct. How would I construct it? Would I just keep drawing, take a ruler and draw lines from x1 until I find a line that is cutting the boundary at 90 degrees, or is there a smarter way of doing it? Exactly, right? I want the smallest distance. What is the locus of points that are at a constant distance from x1? Circle, right? So if I take, for example, something like this, all the orange points have the same distance from x1. Now what I can easily start doing is start increasing this. At some point, what will happen? At one very critical point, I will just touch this blue guy, right? So I'm going to get something like this. Right, so graphically that is what this operation is doing. It is finding me this point over here. Let's call it y. Okay. So in our fancy language, we will call this a L2 ball. Right. So this is if radius r, then I say that this is L2 ball of radius r. Okay. Obviously centered at x1. That is the meaning of this guy. So I'm just going to write down a few properties of this projection operation, which are mostly intuitive, so I won't be stating them via proof. But the first property, if x1 is outside, do you expect that the projection point will be in the interior or on the boundary? On the boundary, right? So y will belong to on the boundary. Okay. Now there was one student who mentioned something about orthogonality or perpendicularity, right? So it is actually correct. So if you look at this tangent point over here, the line connecting the point x1 and the projection y turns out to be perpendicular to, what can I draw at this point? Perpendicular to what would you say? Tangent, right? The tangent at this point. So, okay. Do we already have a geometric object that captures this property of tangency? Tangent cone. Okay. So this guy actually at y, if I sit and construct feasible sequences, take feasible scalars, get a tangent cone, what I end up constructing at this point is a tangent cone. Okay. And so again I'm going to state this without proof that this vector x1 minus y, this vector should be in what relation to the tangent cone? Perpendicular. This is going to be perpendicular to the tangent cone of y. So these are just some simple intuitive properties of this projection operation. Okay. Notice that we are using, I mean I have written all of these properties for convex things. Okay. If the set is not convex, all sorts of strange things can happen, right? So you can imagine, okay, let me not draw it, but you can imagine like weird shapes where a point approaches, okay, let me draw it. Supposing this is my point and my set is like this. Now, strange things can happen about, I may have more than one point, for example, right? Various things can happen. So this discussion is limited to the case of convex sets. And the good news is that many times the feasible set is a convex set. So this, for many engineering problems, it works out that using convex sets is good enough. For example, let us say you're optimizing the power of an antenna in an array. Okay, and your options are only obviously, so what would be the first common sense? So let's say I have a variable p, okay, and I'm trying to do some optimization. What would be the first common sense constraint you would put on the power? Has to be non-negative. It makes no sense to talk about negative power. So this is the first common sense constraint. What else can you think of? Just think of a real life engineering problem. I will have some maximum amount of power that I can work with. I will never have unbounded power, right? So the second common sense constraint would be less than equal to some, let's say m. right? Now, what kind of a set is this? If you sketch it, what kind of a set is this? It is a convex set, right? So if I draw P like this is 0, this is M, this is where this is my feasible set. It's clearly a convex set. So there are 90% of engineering problems will end up having convex constraints. So all the nice properties of the projection operator which I have written, they will hold true. Okay. Now, if you look back here, I've simply defined over here this is the projected gradient descent algorithm, which is fine. I mean, at this point, it's just like I've given you some information. We haven't proved it. Why should this work is the first question that should come to your mind. This looks almost too simple for it to work, right? So so what we'll do is I'll give you a proof of why this works. Okay, so it is your last and final convergence proof for this course that gives us faith that the method actually works, right? So the reason I'm saying this is because you may come up with several very intuitive ideas to solve a constraint optimization problem, but they may not work. You have to also prove that it works, right? So let's look at the convergence analysis of this. Okay, now I'm going to make a little bit of a relaxation over here. I'm going to prove a slightly weaker version of it, just so that the proof is simple enough to understand. Okay, and I'll show you what that weaker version is. Okay, I'm going to make my starting point is going to be obviously gradient descent plus projection. Now in gradient descent, what are the different variants possible for alpha? The step length. I could do backtracking line search. That's fancy. Could I do something less fancy also? Exact line search is even more fancy. I'm going in the opposite direction. I want something simple to start with. Constant. I could do constant line search also, right? Constant line search will just make the method converge a little slower, right? But it is something that works. Okay. So to make this analysis a little bit simpler, I'm going to start with constant step length. That's the assumption we'll make. By the way, in the literature, you will find proofs for all flavors of it, backtracking, Wolf conditions, blah, 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 right? But the proofs are more involved. Okay. All right, so again, we're going to make use of graphs for intuition. Okay, so this is F, and so I'm working with a convex function. Okay, let us say. So a convex function will look something like this. So here is, let us say this is my point X over here, and this is some later point over here, Z. Okay. And the property of convex function, not sets, is what? The function will lie above or below this blue line. Below, right? That's the definition of a convex function. Okay. So let's just say convex function. So if I were to write Taylor's theorem for F, okay. So let's assume that X and Z are close to each other. So I want to write F of Z. By now all of you are experts in this. First order Taylor's theorem, what should I write? First term should be F of X plus, what else? Grad F at what point? X transpose Z minus X. This is first order. What is the error that I am incurring if this distance is, let us say, delta? Right? So there is a higher order term over here which is order delta squared. That is the error that I'm having. Okay. So assuming that we are with the first order Taylor's theorem, we know that so F of Z is over here, right? Okay. So what I have drawn is the line connecting f of x and f of z. Which way will grad f look? Will it be this dotted line or will it be something else? You got the difference? This is just a straight line connecting f of z and f of x, right? If I wanted to sketch grad f, because I've written grad f over here, I want to sketch grad f, which way would it look? Grad f is what? The tangent, right? So it should be the tangent at which point? At x, right? So the tangent is going to be like this. And again, as this is another property of convex functions, that the tangent will be above or below the function in the local neighborhood. Below, right? Because it's like a upward opening cup. So the tangent is always going to be below. Excellent. Okay, so now I'm going to ask you a question. What is this point over here that is marked in orange? In terms of its value, what would you say? That's correct. Anybody else wants to take a guess? How do I arrive at this orange point from what I have already described so far? Yes. Grad f of z. No, grad f of z would be the tangent at the point z. Grad f of x into delta. Are we missing something? Right. So actually, this point that I've written over here is actually this whole thing. Right. This tangent over here plus f of x. Right. I have to move that tangent up. Right. So what this is the linear approximation of f at x. That's what it is. So this is the linear approximation of f at x. This is the graphical meaning of first order Taylor's theorem. Take a point, take the tangent, go along it, that's your linear approximation. Okay. So now that you can see this graphically, so let's ignore this error term on the right hand side. Do you think that we can actually write this now as an inequality? F of z will be greater than or less than? Greater than. It's a convex function. You can see it on the graph, right? This point over here, what is this value? The red dot. This is f of z clearly, right? So it's very easy to see that actually f of z is greater than or equal to fx plus grad f transpose x z minus x. Okay. So I'm just going to write this over here, assuming, or rather assume convexity of f. So before I go through the entire proof, I want to just give you a sketch of what we're going to do. If you remember, we had that Zootendix condition when we had done the previous convergence. So the trick that we had used there was telescoping of a series in such a way that f at the optimal point and f at the initial point was all that was left. If I can make this distance be as small as possible, or I mean bounded in some way, I will arrive. So that's the strategy that we're going to do. Okay. What is the complication over here? The complication is that at each step I have to do a projection. Right? Every iterate has a projection operation and then there's an update, but the update is followed by a projection. So that is different from the usual gradient descent which I had done. So that's something to keep in mind. So in this inequality, am I free to choose x and z any way I want? Right, it's up to me. So what I'm going to do is, I'm going to choose, let's assume that this sequence of iterates converges to some point x star. So let's call that x star, and I'm going to put x is equal to xk. So this is the kth iterate. Okay. So then I will get f of xk minus f of x star is less than equal to grad f of xk transpose x star minus xk. Right. So this is, let's call this as this step 1. Okay, step 1 is setting up this inequality. Right, and this gave me, so this is going to be my starting point. Okay, so just you can see how I can think of this telescoping business, right? They have a f of xk minus f of x star. Just imagine if I had this for many iterations and I summed it up, would stuff cancel out? Right, so that's roughly the direction that we are going in, except xk itself is of not much interest to us. What is of interest to us? The projection of xk. So we have to get in this projection operation somehow, right? So that is going to be my step 2, which is the PGD update. Okay. So the step without projection, I'm just going to use a new symbol for it, y. Okay. So yk plus 1 is simply my xk minus alpha grad f of xk. It should be, no, so I think it's fine, right? On the right hand side, I put f of x, of right hand side of this expression is f of x star. Oh, no, it's correct. Does someone want to verify this? It's correct. I've just flipped them on each, on the other side, right? Okay, so this is our usual gradient descent update. Okay, maybe I'll go to the next page so that I can draw this. So let's say that this is my feasible set. Okay, let us say this is my xk, let us say this is my x star. Okay, and let us say that this is my yk plus 1. Okay. Now after projection, what will happen to yk plus 1? It will fall on the boundary, right? Okay, let's look at that once again. Okay, so let's take this guy and let's put, just substitute away, f of x star is greater than equal to f of xk plus grad f transpose xk x star minus xk. Okay, and so okay, right, so then this is, if I keep it, that's, if I want to keep f of xk there, then okay, so this is going to be f of x star. I want to keep it in x. Okay, so you're right, so there should be, the inequality gets flipped, is that right? Oh, what if I do a little bit of cheating? Okay, thanks for catching it. Okay, so just correct it. This is my projection point, right? So xk plus 1 is obtained by projection of yk plus 1. This is the definition. We also had yk plus 1, as I just wrote on the previous slide, xk minus alpha grad f of xk. Okay. So I can draw a vector connecting, basically I can reach yk plus 1 by joining what? Xk and this minus alpha grad of k, right? So if I draw this, So, in shorthand notation, I'm just going to write the previous inequality f of k for f of xk and f star for f of x star. Okay. This is, I had grad f k transpose and I had xk minus x star. Right, this is what I had. So I'm going to multiply divide by alpha so that all the guys appearing on the graph also appear over here. Okay, everyone with me so far? Now I have two vectors, grad f transpose times alpha, which I have sketched over here, and the other vector is xk minus x star, right? And I have the inner product of these two guys. I want to somehow separate these guys out. Okay, I want to separate them in a way that I can work with them, because if I just sum this, I'm not going to get anything interesting. If I telescope this series, for example, the right hand side summation is not going to be anything that I can work with. So I need to somehow split these guys into separate terms. So a very simple inequality, or not inequality, a way to express P transpose Q. Do we know how to do this in terms of P and Q? So if what is, for example, norm of P minus Q whole squared, what all terms will be there? Think of this. What all terms will be there? P transpose P, Q transpose Q, and a negative P transpose Q and Q transpose P, which are the same. So there's a 2 factor over there, right? So that's a nice way to get this. So P transpose Q will be simply half of norm P squared, norm Q squared, and finally norm of P minus Q squared. Right? So I'm going to take this guy as P, this guy as Q. I'm going to apply this over here so that these guys separate out. Okay. So fk minus f star less than equal to, I'm going to get a 1 by, the 2 will come, so I'll have a 1 by 2 alpha. Okay. First term is alpha grad fk squared. Next term is xk minus x star squared. Okay. And then I'm going to get the difference of these guys. Alpha grad fk minus xk minus x star, right? It gets longer before it gets shorter, so don't worry too much about it. Okay.